Good day to all of you. In the last class, recapping, we discussed the concept of state space averaging using boost converter as an example. The circuit averaging method that we discussed, we also employed it in trying to obtain the dynamic equations for the boost converter, and we stopped at a point just after we arrived at the average large signal model. Now, today in this class, we are going to continue from there. We are going to develop the steady state model, the small signal model, and then discuss on the various aspects about the model from there on. Okay. So, a quick recap, we discussed on the boost converter state space method of obtaining the circuit averaged model. This is the boost converter which we discussed. It contains the input source VG, input current IG, L, two switches S1 and S2, C, and a load current IZ. This is also representable in terms of switches here. It can have an IGBT here or a diode as these two switches, the IGBT being switched during DTS time and the diode comes into action during 1 minus DTS time. And from here we started developing the state equations during DTS time. This was the state equation that we developed, and during 1 minus DTS time this was the state equation that was developed. And then we started combining the equations to obtain the average large signal model. So, the average large signal model is obtained by combining the state equations and the matrices obtained for the DTS period and that obtained for the 1 minus DTS period, and they are time averaged A1 into D plus A2 1 minus D, so on and so forth for all the matrices. And then based on that we obtain the averaged large signal model, which is like this. So, here note that we have used the term R. So, the term R there is basically to have a concept of a bleeder resistance here. So, you have a resistance R here, and to that R in parallel you have a current source attached, and the current source basically gives you the idea of the varying load. The load is an external input to the system, and therefore, that can be considered as one of the inputs. The VG is an external input to the system, so that also can be considered as one of the inputs. And another input that you can consider is the control input here, the D. So, to this you are giving the duty ratio as one of the information signal. This is an information signal, this is an energy signal, this is an energy signal, this is an information signal, and this is also an energy signal. So, you basically have three inputs to the system which you need to observe and understand. Okay, now that we have recapitulated on what we were doing, we shall now proceed from here. So, from the averaged large signal model, we shall obtain the steady state model. Steady state model can be obtained in a simple way, wherein all the derivative terms, all the x dot terms will become 0, which means in the steady state, in the equilibrium state, you do not have the derivatives, and all the variables will take the uppercase forms, that is d will settle at an uppercase D. This is the equilibrium condition of the D. And likewise, Vg will become Vg, Ig becomes Ig, and so on. Okay. So, from the averaged large signal model, we shall mark off this, copy that, and we shall paste it here and edit this to form the steady state model. So, the steady state model is obtained by replacing the derivative terms with 0 and replace the lowercase d's with uppercase D, like this, and these terms become uppercase IL and VC. VG, IZ, V0 and IG are the steady state outputs that we want to get out from the state variables. Now, this becomes the steady state model for our converter. All that we have done right now is replaced all the variables with uppercase values, and we have removed the derivative terms, made it into 0. Now, this is of the form 0 is equal to A x plus B u. Now, here x and u have become uppercase. So, you have a steady state variable and a steady state input variable x and u. X, steady state variable x is obtained from by simple manipulation of these minus B u and then pre-multiply by A inverse. This would be the steady state relationship between the input scaling, the system parameters and the state variables. Likewise, if you want to include the output equation into this, you have, let us say, y which is equal to C x, which is minus C A inverse B u. So, if you want to get the transfer relationship between any two variables, you have y by u. If it were all single variables, y by u would give you the transfer relationship, and that is equal to C A inverse B. However, in the matrix form we do not write it in that fashion. We apply it to specific variables here. Now, here y is equal to C x. An example would be V naught. Let us say V naught is equal to x, in our case was I L and V naught. Okay, so this is what would be C x, and V naught is equal to C, and x is written as A inverse, and you have to take that matrix for which you want the transfer relationship. So, let us say we want with respect to V g, then multiply it with the B matrix corresponding to V g into V g, assuming I z is equal to 0. When you want to get the transfer relationship, you are getting the transfer relationship of an output variable to an input variable, assuming all other inputs are 0. Likewise, you could also get the transfer relationship V naught with respect to I z. Sorry, this is a minus here. C A inverse. Now, the B matrix corresponding to I z. This will give you, and here you assume V g equal to 0. So, this gives you V naught by V g, and this gives you V naught by I z, the output steady state output impedance. Now, take for example this V naught is equal to minus C and A inverse B 1 by L and 0 V g. Okay, we need not calculate A inverse of the all the elements, because this is 0. These two are don't cares. There are values, but we are not bothered in obtaining the values. We shall obtain values only for this portion. So, the determinant in this case would be to find the inverse. The determinant of this matrix is 1 minus d square by LC. Okay. And multiplied by the cofactor, and the cofactor is 1 minus d by L. So, you will land up with L by 1 minus d. You can work it out by hand on paper. Now, this on multiplication gives you one into L by 1 minus d into 1 by L, which is equal to 1 by 1 minus d. Sorry, this is actually A inverse. This is equal to A inverse. I do not have to put that there. So, you have here C, A inverse, this is B corresponding to the Vg input. So, you see that V naught by Vg, which is equal to 1 by 1 minus d, and this is the relationship, steady state relationship that you had discussed very early in the course. So, like that you could get the steady state relationship of any output variable to the input variable. So, proceeding from here, we can now try to get the small signal model. So, the small signal model is obtained by substituting in the average large signal model for every variable a steady state part and a small signal variation about the steady state or equilibrium point. V naught is equal to V naught plus V naught hat. So, the variation about the equilibrium point we are indicating by hat. Vg is equal to Vg plus Vg hat. Iz is equal to steady state part plus this, and you have IL, which is having a steady state part plus IL hat, so on. So, we try to make these substitutions everywhere. So, when we try to make the substitution, there will be new terms which will be coming in. So, this will get substituted as IL dot plus IL hat, Vc dot plus Vc hat. Now this portion becomes minus d hat, d plus d. Likewise, minus d hat, and these variables will become also IL plus IL hat, Vc plus Vc hat, I will Vg plus Vg hat, and Iz plus Iz hat. And likewise the output equation. So, the output equation, you could take either V naught as the output, V naught plus V naught hat, or you could take Ig as the output. IL plus IL hat and Vc plus Vc hat. Okay. So, still the small signal model is not complete. This is actually having small signal plus steady state included. Now, we have to split this, remove the steady state part. We have to split this and remove the steady state part, and then you get the small signal part. So, we know that the IL dot, Vc dot are the derivatives of the steady state. So, they are apparently 0, and therefore, we can remove that part, and we have basically the small signal dynamics. And here we shall perform a few operations. For that, let us take this portion into a new page, copy that, yeah. Now, the operations that we shall perform on this is very simple. We split these matrices. So, 0 minus 1 minus d by L, 1 minus d by C, 1 by RC, and IL Vc plus 0, 1 minus d by L, 1 minus d by C, 1 by RC, and IL hat VC hat. So, this matrix is split into these two parts. Of course, we have to yet consider this too, small d hats. So, that will come as 0 d hat by L minus d hat by C 0 I and V naught. So, what we shall now do from here is to use d hat. We will take out d hat and push the steady state components inside. So, this actually would become I by L, sorry, V naught by L, that is, I am trying to link these two and these two minus I by C d hat. So, that can be written in this form here. Now, this is one of the steady state parts, that is the steady state part, the AX part, steady state AX part, and then you have a steady state B steady state part here, BU part. So, that part and this part is set equal to 0, because the steady state parts are equal to 0, because AX plus BU equal to 0. So, therefore, this part and this VG into 1 by L 0 matrix become can be eliminated. So, from here if you simplify, you land up with the following: IL hat dot VC hat dot. So, these are the terms 0 1 minus d by L 1 minus d by C minus 1 by RC, and you have only the small signal components. This is corresponding to, this corresponds to this portion plus V C by L minus I by C into d hat that corresponds to this portion plus 1 by L and 0 Vg hat that corresponds to this portion, and finally, this portion we incorporate it in here 0 minus 1 by C Iz hat. So, this becomes the state equation of the small signal model, and plus you can have your output equations. So, the output equations would be of this form 0 1 IL hat V C hat. So, this could be one for one equation, or you could have output as Ig, the input current itself, which is of this form. So, either you could have this or this. This output equation can also be combined together in the following manner. You could have Ig hat like that, one 0. So, this also results in the same output equation, y is equal to C x. You have x dot hat equals A x hat plus another matrix, let us say m d hat plus or we will put it this way. B1 d hat plus B2 Vg hat plus B3 Iz hat. You could also combine the three inputs in the following manner. So, what we shall do, these three inputs we shall combine in this fashion. To make it into a common input, wherein you are having three inputs, Vg hat, Iz hat, d hat, and Vg hat 1 by L, then you have 0 minus 1 by C, and then V naught by L minus IL by C. So, this this would form the B matrix and the U vector. So, this model here would represent the small signal model of the boost converter. So, summarizing the process, we first from the circuit depending upon the temporal modes, operative modes, that is dTs 1 minus dTs time duration, split the circuit and obtain the separate models for each of the temporal modes. That is, you will have A1 x plus B1 u, and that would be x dot, and then you would have A2 x plus B2 u. Then you can combine them by making a averaging in this fashion. Likewise for the output equations also. Once you have combined them, you have what is known as the averaged large signal model. And then from the average large signal model, the derivatives of equilibrium variables or states are set equal to 0, and all other variables represent steady state quantities that is d becomes d, x becomes x, y becomes uppercase y. They represent the steady state quantities. So, you will get Ax plus Bu. Substituting these in the average large signal model, you will get the steady state model. After you have got the steady state model, the average large signal model is split. Every variable has a steady state term and a small signal term, a small signal variation in the neighborhood of the operating point. So, this average large signal model is split up with these. Remove the steady state portion and to the remaining terms apply the constraint that the product of small signal terms, like example this, is insignificant and this is very small and can be neglected. Take only the first order small signal products and you will end up with the small signal model. And this small signal model has to be used for your control or controller design. So, if you look at our plant, which is for example in this case the boost converter, and let me say the controlled converter is something like this. We have a power input, this is called Vg, and we have an output, we are calling it as V naught. We have a control input D, you also have controlling the load Iz, which is coming as an external input, and this is a disturbance input. Because this is not a controlled input, the load is not under your control, it is an external disturbance. The load can change depending upon the application. So, therefore, it is considered as a disturbance input. Vg itself is an input, because the variation in Vg is to be taken into account by varying d, and d indirectly varies Vg to the system. So, you have, let us say, one output and 3 inputs. And of which D is the control input. This is called the control input. So, when you want to design, you need to have a transfer function of the system V naught with respect to D. So, if you take the transfer function, which is the Laplace transform of the output by input, you are required to obtain V naught S by ds. Or if it is a small signal model, V naught hat S d hat S. So, this is the control transfer function model that you will be using. Now, let us see how we go about getting the transfer function from the state space model. You know that the state space model is given by A x plus B u and y is equal to C x. Now, if you take this, the derivative term, take the Laplace transform. So, you have S x s A x s plus B u s, y is C x s. So, from here you have S I minus A inverse B u s is x. So, you actually have an I here. S I minus A, push it to the other side, S I minus A inverse B u s. Now, this you substitute here. So, what do you get? You will get y of S, which is C S I minus A inverse B u s, and this is how you would obtain the transfer function. So, looking at that, CSI minus A inverse B US. If you want to obtain V naught as your output variable and input variable is D hat, the B will correspond to only that portion corresponding to D hat. So, if you take the small signal model here corresponding to D hat, you have this column of the B matrix. So, only that column need to be considered because transfer functions are for single input single output only. So, that is V c by L and minus I L by C. And Si minus A inverse is the A matrix which is the same for all inputs, and that can be operated upon to obtain the transfer relation between this and this, or V naught hat by D hat is equal to C Si minus A inverse B. Okay. If we consider B the B matrix as columns. So, let us say B column 1, B column 2, B column 3. So, B column 1 we used for Vg, B column 2 is used for Iz, B column 3 is used for D in trying to obtain the transfer functions. So, you use B column 3 in this specific case, or if you need to have V naught hat by Vg hat, you would see Si minus A inverse B column 1, or if you would like to have V naught hat by Iz hat load disturbance with load transfer function for load disturbance, you will have Csi minus A inverse B column 2 and so on like that. So, there are certain names which have been given and you will find them in the literature, and these are common names. So, if you get the transfer function Vg hat by let us say Ig hat Laplace transform, which is obtained by C Si minus A inverse no, these are general terms, let me wipe it out. This is called the input impedance transfer function at d hat equal to 0, I z hat is equal to 0. How do we obtain this? We know that I g as an output is given by a c which is 1 0 like this and x, and therefore we can obtain it in this fashion: S I minus A inverse and the input B 1 for Vg hat. So, Ig by Vg hat is obtainable by this. Inverse of that will give you the input impedance. So, this would give the input admittance. Then another common transfer function is V naught hat by Iz hat Laplace, and this is called the output impedance. Now, at the other two inputs being 0, that is d hat is equal to 0, Vg hat is equal to 0, Iz hat is the disturbance input. So, Iz is the input, V naught is an output. So, this is directly obtainable using C Si minus A inverse B2. Another transfer function is V naught hat by Vg hat. This is the input output voltage relationship. This is also called audio susceptibility. See, D or D hat is the control input. That control input is actually changing Vg, and Vg hat is also one of the inputs, and variations in Vg can also get reflected as changes in the output, and these are low frequency or low signal variations, and they are in the audio range or the low frequency audio, and the regulation or susceptibility of the circuit to these low frequency disturbances is called the audio susceptibility, and that is why such a name is given, and this is at the D input being 0 and the Iz input being 0. So, this is also directly obtainable: Si minus A inverse, this is the B1 matrix. You have another transfer function. This is the control voltage gain at Vg hat equal to 0, I z hat is equal to 0. And this is obtained, say D is an input, this is an output, C S I minus A inverse B3 column. Likewise, you saw that you could have another output, which is the Ig, the input current. So, if input current is an output and it is getting controlled by the control input D, then it is called control current gain. And this again at Vg hat equal to 0, Iz hat is equal to 0, and this is calculated as C matrix changes Si minus A inverse B3 column. So, this is how you would get these various transfer functions. So, just with one modeling you can get various transfer functions, but for control remember that you are doing the control with duty cycle. If you are doing output voltage control, you will be using this transfer function. If you are doing the input current control, you will be using this transfer function. Okay. Now, in the till now we have done some derivations on these converters through the process of circuit averaging, and what we have done is on paper considered the switches as rather ideal, and then found out the average large signal model, the steady state model, and the small signal model. And from the small signal model you can derive various transfer functions. So, you have the state model and the various transfer functions that can be derived and used for analysis purpose and control purpose, especially the transfer function with respect to the control input, that is the duty ratio, will be used for control purposes. You can do either voltage control or current control. More or less this is the approach for almost all the converters, and I suggest that you practice with different isolated and non-isolated converters in the same manner. In the next class we will try to use MATLAB and probably also SPICE to do some simulation and see how these plants perform, so that it will become more intuitive and more easy for us to understand when we take up the controls. Thank you.